So as promised before, we're going to do some more interesting stuff with our movie ratings data from the Movie Lens dataset. And let's actually compute movies that are similar to each other. This is a component of something called item-based collaborative filtering. Fancy sounding thing, but you'll see the concept's not as hard as it sounds. And along the way, we'll introduce the concept of caching your RDDs and persisting them, something you need to remember to do for best performance if you're going to use the results of an RDD more than once. So, what do we mean by item-based collaborative filtering? Well, it's an algorithm that's used for movie recommendations or recommending any kinds of items, really. Basically, the idea is we try to find relationships between items, in this case between movies, based on customer behavior or user behavior. So if we see two movies that users tend to rate together similarly, then we might say there might be some sort of connection between these two movies. And if you like one movie, maybe you'll like these other movies that are connected to it through that user behavior data. So using that technique, we can build up features like this one on the Movie Lens website, where they have their own recommender system, and the same basic idea can be used to recommend anything on any website you can think of. It's used in e-commerce, for example, in a lot of different places. Let's go into how it actually works. So basically what we do is we start off by finding every pair of movies that were watched together by the same person. So any movie that was watched with another movie by the same person goes into a big old bucket of movies that were watched together by the same individuals. And then what we do is we take all the users who watched both movies and we compare their ratings to each other. And using those rating vectors that are associated with each movie pair, we can then try to compute how similar are these two movies to each other. And that's just one way of doing it. There's like countless ways of doing recommendations. This is just one algorithm that works well in some situations. So it'll make more sense with an example here. So let's say, for example, this lovely lady here watched Star Wars and The Empire Strikes Back, and she loved them both, gave them both 5 stars, okay? So already we know that these two movies were watched together by the same person at some point. Now let's say this edgy-looking guy here with Mr. Mohawk also watched Star Wars and The Empire Strikes Back and also loved them both. Both got 5 stars. Now by comparing the behavior of these two different people who watched both of these movies, we can say, okay, well, people tend to rate these two movies in the same way, and they tend to watch them together. There might be a lot of people who watched these two movies and thought the same of both. So that might tell you maybe these two movies are similar to each other. Now, given that information, if we know that Star Wars is similar to The Empire Strikes Back, let's say Mr. Hipster Mustache Man here comes along, and for some bizarre reason, he lives in this strange universe where he watched The Empire Strikes Back but was completely unaware of the existence of the first movie of Star Wars. But we can help this man. We know that through the behavior of these other two people that these two movies have a connection. They've been rated similarly by many people. And we can use that relationship to say, okay, if you like The Empire Strikes Back, you'll probably also like Star Wars. And given that you've never seen it before, that might be a really good recommendation for a movie for you to watch next. So that's all there is to item-based collaborative filtering. It sounds very complicated, but it's not that hard to wrap your head around. Basically, we look at people who viewed the same pairs of movies and rated them similarly. So if a given pair of movies has a similar set of ratings from many users, we can say, okay, these two movies are probably similar to each other. And it's important to point out, though, it doesn't necessarily mean that these are good movies, right? If both of these people saw both of these movies and hated them, gave them 1 star, they would still be considered similar to each other and similarly bad, right? So you have to be careful of that when you're interpreting these results. You don't want to end up recommending bad movies to people, and we'll talk about that more later. So how do we make this into a Spark problem? Well, here's our general strategy. And again, this is an example of taking a complex algorithm that doesn't seem to lend itself to Spark initially, but framing it as a Spark problem that we can attack with mappers and reducing functions and use that to actually distribute this out to a cluster and deal with massive data sets. So here's the approach. We're going to start by mapping the input ratings data set into this structure here, where we have a key of user ID and a tuple for the value of movie ID and rating. So we have these movie rating pairs associated with every user. So for every movie viewed by a user, we're going to have that movie and the rating for that user. And then we're going to blow that out to find every movie pair rated by the same user. And we can do what's called a self-join operation. Remember, you can do these database operations on key value RDDs, join being one of them. If we join on itself, we end up with a list of the user ID and every movie rating pair that they actually watched. So that gives us back every possible combination of movie ID 1, movie ID 2 for every permutation of movies that that user watched. Okay, so this blows out really quickly. You know, this is where the big data comes in, because once you start doing this factorial stuff, things can get out of hand pretty quickly. Okay. Now, to try to rein that massive amount of data in, because we're looking at every possible combination of movies that were watched together by every person, it's a lot of information. We're going to filter out any duplicate information at this point. So movie ID 1, movie ID 2 is going to be the same as movie ID 2, movie ID 1. So in cases where we have the same movies just in the opposite direction, we'll filter out one of those cases. Cases where we end up with the same movie in both sides of the pair, we can get rid of that as well. And that just narrows down our data a bit. Now the next step we're going to do is treat the movie pairs themselves as the key, because what we're trying to find is similarities between pairs of movies. Okay? We want to try to evaluate, is this movie similar to this other movie or not? So to get to that point, we need to make these movie ID pairs the actual key, and the value will be the ratings associated with those movie pairs. So every pair of movies that was rated by the same user will end up in one of these rows where we have a movie pair and a rating pair from that user's behavior. And we can then use group by key to munge together all of the ratings found for this pair of movies across the entire user set. So at this point we have a pair of movies, we have all of the ratings from everybody who watched these two movies together, and we can compare the vectors of ratings data for these two movies together and use that to measure the similarity between those two movies. So at that point we have our results. We can measure how similar are these two movies to each other based on user behavior, and sort them, save them, or display the results, whatever you want to do. So in this particular example, we're going to introduce a new concept called caching, or persisting your RDDs. And as we go through the code, you'll see that we're going to produce an RDD of our final results and query it more than once. Anytime you do that, if you're performing more than one action on the same RDD, you need to explicitly tell Spark to cache that RDD so it doesn't go off and try to recreate it from scratch the second time around. Otherwise it might. You know, whenever you call an action, remember, it goes off and builds up that directed acyclic graph and figures out how to run everything and actually kicks it off. So if you create an RDD, run one action on it, and then another action on that same RDD, it might go off and recreate it again. To prevent that, we have this cache function or persist function that you can use to make sure that it keeps a copy of that RDD around so that if you need it later on in the script again, it can go back to that copy of it instead of recreating it all from scratch. Okay? What's the difference between cache and persist? It's pretty subtle, actually. Persist gives you the option to cache it to disk instead of just to memory. So if you want to deal with, if you're worried about fault tolerance and nodes failing on you and being able to recover from that as quickly as possible, persist might be a better choice, but obviously it requires more resources to get to that state, so a little bit of a trade-off there. I use cache myself more often than not, but you can use persist if you're paranoid. And with that, let's take a look at the code and actually run it and start to get some interesting results.